Hello everyone and welcome back to the channel. Today's video is in knock control, probably one of the smartest and most complex systems in your car. I'll show you how it works and how it's able to tell apart between actual knock and harmless engine noise. But before diving in, let's define what knock actually is. In gasoline engines, the combustion is triggered by the spark plug, and in the best case scenario, you're going to get a smooth combustion curve like the one shown here to the left. Sometimes, however, the mixture can ignite the wrong way, and we experience something called auto ignition, and it results in very aggressive pressure spikes like the one shown here in the center, or even more like the one shown here to the right. What happens at this time is that you have the combustion wave started by the spark plug, but somewhere else in the cylinder, you get auto ignition. So you have these two pressure waves traveling towards one another, and at some point they collide. And that's what causes the very distinctive pinging or rattling noise. When knock happens, it's like hitting the top of your piston with a hammer. If this happens consistently, you're going to get damage to your pistons, your rings, or it could even crack your cylinders. If you're wondering how knock sounds, grab your mouse and click the button. Nope, I'm not kidding. That's how knock sounds from the outside. Okay, but what exactly causes knock? There are multiple things that contribute to it, but I have a list here of what I consider to be the most common ones, starting with low octane fuel. After all, octane is the measurement of how much pressure and heat a fuel can take before auto ignition. So it makes sense that the lower the octane fuel, the less resistance it has to auto ignition. So for example, let's say that you have a vehicle that it is designed to take premium fuel, but you add regular fuel to it. In that case, you are more susceptible to experiencing knock. Second, high engine temperature. Pressure and heat go hand in hand with each other. So if you have this additional heat in your engine, you are promoting knock to occur more easily. Third, over advancing ignition timing. I have a graph right here with three different ignition timing. In green, we have essentially very late ignition timing, so much that the piston during the power stroke can run away from the expanding combustion. In yellow, I have the best case scenario where the maximum pressure in the cylinder occurs at top dead center or soon after top dead center. In red, we have a knock occurrence that was triggered by a very premature combustion spike. In this case, your piston could even be fighting during the compression stroke as it's traveling up, and we have the combustion already happening. And lastly, we have lean air fuel mixture. By nature, lean combustion burns hotter. And again, if you have hotter temperatures, you have more pressure, and that's the perfect recipe for knock. Modern vehicles are extremely smart and they can detect knock the moment it happens and fix it even before you notice it. But how, you ask? That's an excellent question. Let's break it down step by step. You may or may not know this, but your engine has ears. There are these round devices bolted on top of your engine called knock sensors. Every time that a vibration occurs, it makes a signal. The bigger the vibration, the bigger the signal. But here's the thing, there are constantly vibrations going on in your engine caused by piston slap, injectors going on and off, and valves opening and closing. So how is it able to tell apart between knock and just noise? The first thing that you need to understand is that your ECU is not looking for knock 100% of the time. It only does it at a very small frame called the knock window. This window happens shortly after the spark plug fires, typically between 10 and 40 degrees after top dead center, because this is where knock is more likely to occur. This helps the ECU to only focus in the vibrations that are potentially knock. So let's say that your knock sensors did pick something up within the knock window. There could still be a lot of noise in between that frame, a lot of ticks, a lot of pings, a lot of bangs. So the first thing that your ECU does is that it passes that signal through a filter, and it typically keeps everything between the 6 and 10 kilohertz. Everything else is filtered out. Once the signal is clean, the first question that the ECU asks is, how loud was it? Was it a small vibration? Then it was probably nothing. Was it a strong vibration within the knock window? That's a red flag. That could have potentially been knock. Newer ECUs are super smart and they don't just ask, was that loud? They also ask, did that sound like knock? Knock has a very distinctive signature shape, usually very sharp, very sudden, and very spiky, versus most of the other noises coming from the engine. They tend to be a little more rounded. So it compares the two waveforms in order to make a judgment if it is knock or not. And this helps a lot to reduce false positives. Now let's talk about knock threshold and how ignition timing is adjusted. Now that the ECU has all of the information that we discussed previously, it needs to make a decision as to what to do. Here's an oversimplification where the ECU is counting the number of knock occurrences versus a certain amount of cycles in the engine. If this knock threshold is exceeded, then the ECU reacts by delaying ignition timing. This reduces pressure in the cylinder, and typically that helps to reduce or stop the knock from continue happening. Something even cooler is that it can do this cylinder by cylinder. So for example, if you're only experiencing knock in cylinder 3, it can only delay ignition in cylinder 3. If no more knock is detected over time, then your ECU will try to bring back your ignition timing closer to the base timing or the original timing. However, if you continue to experience knock, then your ECU will delay ignition timing even further to try to eliminate it. Let's review what we have learned so far using this practical example and this fictional ignition timing map. Let's say that you're driving down the road at 2000 RPM by 40% load. The original timing is 21 degrees before top dead center, but for whatever reason, knock control is pulling 5 degrees. That means that your actual timing is 16 degrees before top dead center. If you continue driving and you find yourself below the knock threshold, your ECU will advance spark, and that means you'll be closer to the original 21 degrees. However, if you continue driving and you continue to experience knock and you're above the knock threshold, then your ECU will pull spark, delay it, and that means that ignition timing will be even closer to top dead center. If you continuously experience knock at very specific conditions, let's say at some RPM and load, your ECU will start to remember and save this information. That way, in the future, it can take preventive action and delay spark under those conditions in order to protect itself. Some ECUs take that data and apply it every time that you start the car. And if you want to delete it, you would have to do something like disconnect the battery. That's why your car may feel sluggish after a bad tank of fuel. More than likely, you experience knock, the ECU saved that information, and it's going to take a couple of good tanks in order to relearn and bring the performance back to where it should be. So now you know. There is a lot more than it meets the eye when it comes to your ECU keeping knock under control. It's a complex dance between sensors, signals, and software in order to keep your engine safe. If you found this information useful, hit the like button, subscribe, and send me any questions that you may have. See you in the next one.